Uh, okay, hello everyone. In the previous lectures, we learned about recent trend for mutation-based fuzzing techniques, where the trend is the transition from the program-agnostic fuzzing to program-adaptive fuzzings. In particular, we focused on learning the optimal seed mutation strategy in the mutation-based fuzzers, such as MOPT and CM fuzzers. So in this lecture, we will continuously learn about another key components of the mutation-based fuzzing, seed selection strategies. So okay, let's start with this week's lectures. In today's lectures, I will start by introducing a well-known research topic for mutation-based fuzzing, which is learning-based seed selection strategies, and then move on to another approach for gray box testing method, which is called generation-based fuzzers. Like seed selection and seed mutation strategy for mutation-based fuzzings, there are two key components for generation-based fuzzings, which are well-structured grammar generation and smart test case generation from a given grammars. Okay, before introducing these topics, I will start by reviewing a recent trend in the mutation-based fuzzing we have learned about last time. In the previous lectures, we learned about a recent trend in the mutation-based fuzzings. The recent trend can be seen as a transition from a program-agnostic fuzzing to the program-adaptive fuzzings. In particular, we have focused on learning adaptive seed mutation strategies such as MOPT, and where these strategies are adaptively changing depending on the target programs. So unlike the last time we focused on seed mutation, today we will focus on another key component of mutation-based fuzzing techniques, seed selections. At a high level, seed selection strategy has two different rules. First, this strategy will determine which seed from the pool to select first. And second, this strategy also decides to the number of mutants generated from the selected seed, which is also known as power scheduling problems. Okay, first, let's record the basic seed selection strategy for AFL. AFL first loads the initial set of the seed input into a queue and then simply select the seeds in order from the queues. For example, in this picture, AFL will load 5 inputs in a queue and then simply select the first seed S1, and then it will choose select S2 and S3 and S4 and S5 in orders. Think about it. So this sequential seed selection method may not be effective when testing real-world programs. This is because the potential of each seed will be differently typically. More specifically, the potential refers to how effectively mutants generated from each seed will improve code coverage or detect many bugs. For example, let's assume that the number in the lower left corner denotes the expectation values for each seed potentials. For example, this expectation value of the seed 3 is about 10,000, while the expectation value of seed S1 is 10. Generally, a good strategy will prioritize seeds that are having high expected value, thereby maximizing code coverage and the number of found bugs. Therefore, for these 5 seeds, the highest performance can be expected when seed S3, S4, and S2, and S5, and S1 is selected in the order sequentially. So in this time, let's record the havoc stage in AFL. As we learned before, in this stage, AFL aimed to apply multiple operators to mutate the seed inputs. So AFL takes as input the seed S1 selected in the previous stage, and then randomly determines the number of mutants generated from that seed, in this case, M. So as in the previous explanation, it will be also not effective to determine that number randomly without considering the potential of each seeds. So for your interest, in AFL, all mutation-based fuzzing research, the energy usually denotes the number of generated mutants for the each series. Anyway, we should give the opportunity to generate more mutants to a promising seed, and we should generate fewer mutants for unpromising seeds. So if S1 is promising seed, we should assign more energy to the seed to generate more mutants, like 10,000 mutants. Otherwise, only a small amount of energy, such as 100 mutants, should be assigned to the dead seeds. So this problem is called the seed energy allocation problem, or power scheduling problems. Again, say there exist two main research topics. First, when testing real-world programs, the number of candidate seed accumulated in the seed queue will usually be hundreds to the tens of thousands. So in this situation, the first research topic is how to prioritize the seed to generate mutants. And the second topic is how much energy to allocate from the selected seed. This is because AFL usually heuristically assigns hundreds to tens of thousands mutants for each series. Usually in mutation-based fuzzing, the seed selection researchers try to solve these two problems simultaneously. And to solve this seed selection problem, I will briefly introduce a state-of-the-art fuzzers, namely EcoFuzz, published at Eugenics Security 2020s. The motivation of the EcoFuzz can be predictable. The motivation is to allocate too much energy to bad seeds in terms of code coverages. More specifically, a bad seed means that the mutants generated from that seed only cover frequently reached branches. For example, let's first look at the table on the left. The table shows the total number of reached times for each branch during fuzzing so far. And as you can see, the branch B1 is only covered twice so far, while the branch B3 or B4 are covered thousands times during the fuzzings. That is, these branches are frequently reached branches. In these situations, suppose that thousands mutants generated from seed S1 covered only branches B3, B4, B5. That is, the mutants of the seed S1 covered only frequently reached branches. So it would be better to allocate less energy to these bad seeds, such as S1. And conversely, the mutants generated from the S2 succeeded in covering the rarely reachable branches such as B1 and B2 in this case. Therefore, it makes sense to allocate a lot of energy to this good seed for achieving the high code coverage or finding subtle bugs. So EcoFuzz presented a novel seed scheduling algorithm that intelligently determines seed selection and seed energy allocations. At a high level, to achieve this, EcoFuzz transformed finding a good seed selection and energy allocation strategy into serving a domain-specific learning algorithm, which is called to a variant of adversarial multi-armed bandit algorithms. First, let's considering the classical multi-armed bandit problems. We can transform the arms of the multi-armed bandit problem into the seeds of the mutation-based fuzzing. Likewise, the selection of the arms corresponds to selection of the seeds. And reward can be defined as finding a new paths or branches. And the general goal, which maximizes the reward, can be changed as maximizing the path coverage for mutation-based fuzzers. So as you can this transformation, this multi-armed band problem seems to be fit well with the seed selection strategies. However, they tackle that these two assumptions of the classical multi-armed bandit algorithm do not match the seed selection strategies. More concretely, the first assumption of the classical one is that the number of arms is fixed. But recall the process of the mutation-based fuzzing as shown in the figure below. Through the interaction of the seed selection and the seed mutations, the interesting mutants are continuously added to the seed queues. That is, in the mutation-based fuzzing, the number of seeds to select continuously increasing. And the second assumption is that the reward probability for choosing one single arms is fixed. However, this is also not suitable for the mutation-based fuzzings because as testing time passes or the more test cases are executed, the probability of discovering a new path will be decreases. For example, look at the graph on the lower right. In this graph, the x-axis is the number of test cases executed so far, and the y-axis is the number of covered branches. Of course, the branch coverage will be higher when we execute 250,000 test cases than when we execute only 50,000 test cases. So the probability of covering new branches will decrease the more we executed the test cases. So that is the probability of finding new paths should be decreased when testing real-world programs. So to handle this inappropriate assumption of the classical multi-armed bandit problems, EcoFuzz presents a domain-specific learning algorithm, which is a variant of the adversarial multi-armed bandit problems. And I will skip the detail of these algorithms.